When you fire a single photon, or even a large particle like a buckyball toward a wall with two thin slits and place a detector screen behind it, something strange happens. If you don't place any device to observe which slit the particle goes through, you'll see an interference pattern on the detector. This is the familiar striped pattern of waves interfering with themselves, like ripples in a pond. But if you do place a detector at the slits, if you watch the particle as it travels, then something changes. The interference pattern disappears, and what you get instead is a pattern of two bright blobs behind each slit, as if the particle behaved like a solid billiard ball. Standard physics explains this using the wave function, a mathematical entity that contains all possible outcomes. When the particle isn't observed, it exists in a superposition of possibilities. It goes through both slits at once. The mystery is, how does simply observing the particle collapse its wave function and erase the interference? In traditional quantum theory, this collapse is non-deterministic. No one knows exactly how or why it happens. Now let's reimagine this with QIH. Here, the universe is built not from particles or waves, but from spinning vectors of light encoded on Planck-scale detectors, each the size of the smallest meaningful unit of space-time. These detectors are qubits, and each spinning light vector on them is a quantum state vector. In this model, the photon doesn't fly through space as a little ball. Instead, it projects itself outward as an angular frequency, a kind of spinning light-based slope, onto a lattice of these spinning detectors. These spinning projections interfere with each other on the detector screen behind the slits. The interference isn't just mathematical, it's physical geometry. The angles of spin and projection actually determine the brightness or darkness on the screen. Now, if you observe the photon at the slits, what's really happening is that the light from the photon interacts with one of the qubits directly. This locks the orientation of that spin, like freezing one direction on a compass. When this happens, the projection loses its ability to interfere with other possibilities. In standard quantum mechanics, you are told that measurement collapses the wave function. In QIH, measurement is the collapse of a projection caused by a light interaction that fixes the angular slope of a spinning vector. So when you see an interference pattern, what you're witnessing is a holographic imprint of many possible spinning vectors overlapping with each other. And when you see two blobs, what you're seeing is a single light clock vector that's been locked into one direction. Quantum mechanics gives us the probability of what you might see. QIH tells us what is actually happening underneath that probability. Spinning light clocks interfering with themselves in a dance of projected geometry. QIH shows that the standard model is not wrong, it is just incomplete. The wave function isn't magic. It's the result of deeper geometry, spinning vectors casting shadows onto the fabric of space-time. The double-slit experiment, then, isn't spooky at all. It's a cosmic holographic projection of slope and spin. Reality itself drawing interference patterns in the dark with light.